and welcome back to Energy Mechanics, Part 3, with more spinning. So what we're going to look at is this object is moving, and it's moving in a circle. So before, when we talked about kinetic energy of a block, we were always looking at its center of mass, and it moved. However, if we look at this as it's spinning in a circle, its center of mass doesn't move, but it's still moving, so it's got to have energy. So what do? Well, let's look at this tangential velocity and relate it to its motion about the center, or angular velocity. Now we know that the relationship r omega equals tangential velocity. All right, we plug this in there, and we get this new term. This will be our rotational kinetic energy. Turns out this piece right here is very important. And it's so important, we give it its own name, moment of inertia, or an object's resistance to rotational changes in motion. We'll show you this in a little bit. What happens if there's more spinning things? Well, just like when you had multiple blocks moving around, you just add the pieces. Except now we're adding these r squared omega terms, so where the mass is going to matter, which, spoiler alert, we're going to get to that point a little bit later. And you get this summation. Now, all of these have the same angular velocity, because they're all rotating about this piece. So if this one goes this far, this one also rotates through that angle, and so is that one. So linking them to omega in a spinning system is great because all the pieces are rotating with the same angular velocity. We can also integrate. Anytime you see a sum, you can start thinking integration, where r is the distance from your axis. So if this is rotating in the center, that would be r. And you add up all these little mass points. If you want to experience this, where the mass is matters, grab something. Grab your laptop, maybe not your laptop because you're watching a video, but a book. Grab it around the middle and try wiggling it back and forth. Try rotating it. Same thing. Grab it here. Try rotating. And you'll notice one of them's more difficult. As more mass gets farther away, it gets harder to start and stop spinning. That also has a higher moment of inertia. So if we look at this, if that rod, if you were grabbing it by the middle, 1/12. You grab it by the end, 1/3. Oh, grabbing it around the end, well, that book has a higher moment of inertia. That's why it was harder to angularly accelerate. This is in Appendix D-2. We've calculated a lot of these for you, and you will have access to this, but it's good to know. And now for a couple other fun theorems. First is the parallel axis theorem. So if your center of mass isn't exactly where it's rotating, so this is a ball and you'd be spinning it around a circle, like a tetherball, all right? This center of mass is just your regular center of mass or rotating around the center of mass for a solid sphere in this case. But this, the radius is 1 meter, and then you're 2 meters out, so this is the total distance to the object's center. So all you did was displace the center of mass of the object, and then you add it to its rotational, regular mass, if it was just rotating about its own center. This gives us two wonderful things. First off, now we have translational kinetic energy, mv, and it's associated with the center of mass. Then we have this rotational, 1/2 I omega squared, associated with rotation. And finally, this idea of effective mass. So now we've got two types of kinetic energy, and all we mean by effective mass is just the total resistance to an object's acceleration. It's in the denominator, it's a little clearer in an example, and we'll show you what that looks like here in a minute. And by minute, I mean now. So this ball is rolling without slipping, which means it's going to get some angular velocity this way, and its center of mass is going to go to the right. We're going to relate these, it's a condition, it's very important. And we know that it has some translation because its center of mass is moving, and rotation because it is in fact spinning. Translational kinetic energy, what we've been dealing with. Rotational is this brand new I omega squared term. And now, well, what do we do with this? Well, we know the rotation moment of inertia for a solid sphere. We plug that in. We use the condition for not slipping, which is your translational velocity equals r omega. This is very important because a lot of times you want the omega here and omega here. Now we only have one variable to worry about, which is better. Again, one of the hallmarks you should be looking for are ways to connect. And this condition without slipping is a great way. Let's look at this block falling now. So, important to note, the pulley its center of mass is stationary. It's not moving, which means stationary, which means it's only going to have rotational kinetic energy. This block is just falling. It's not rotating, so it's only going to have translational kinetic energy. So we're going to start, again, with our energy experiment. We're going to find the velocity. When you find velocity, you're interested in delta K. All right? So look at change in energy if you're interested in velocity. Or conservation law. Sorry, we're in a conservation law. And now it's translational, rotational in our potential. The block is just falling, but not rotating. The pulley, or the disk, is just spinning, but not falling, center of mass-wise. And then this is block 1, because that's the only piece that center of mass is falling. We plug in our numbers, go through, and again, since I'm interested in velocity, I convert them all to translational velocity, because that's this. This is vt, which is also how fast this is unwinding. We're going to assume that r is constant, that it's not going to change. Now, same thing, I've got vt, I can group terms, keep on grouping terms, go math, and then you get this nice expression for velocity, the tangential velocity, how far this falls. Notice that this also depends on how big that pulley is. So that matters. If you have a more massive pulley, it's not going to fall. Well, have a more massive pulley, it's not going to fall as fast. Interesting. And now we're going to look at acceleration. When we look at acceleration, we generally write the full expression for energy. Notice this is not delta E, this is just energy at any point. So I write this 1/2 mass m squared. This is the I of the cylinder. It looks like a disk, which is why we used I disk. You only care about what it looks like from the point of rotation. And we get our expression for E. Notice I grouped these terms again so that I could group them here. Now to find acceleration, we're going to take the derivative with respect to position. And the reason you do this is because after we apply, split this into two parts, where this is A and this is 1/v, we will cancel out. V will go away. Oh, look, and we'll cancel this 2, make that a 2, and cancel that out. And cancel, of course, I mean factor out. So now, oh, wait a minute. That's interesting. That's what's informed. This could be its resistance to acceleration. So here's the expression for acceleration. And this denominator right here, what's in the bottom? This is your effective mass. So this would be what's relationally linear relationship between what's pulling that object down. And down here, that's your effective mass, the resistance to the object's acceleration. Hope that helps. I will see you in class.